Work means different things to different people because we all have very different jobs to do each day. However, in physics, work has a very specific meaning. It is the change in energy which comes about when a force moves an object over a distance. The work done on an object is defined as the product of the component of the force and the displacement of that object. We use the formula work done, W, is equal to the magnitude of the force F times the magnitude of the displacement times the cosine of the angle between the force and displacement. Work and energy are scalar quantities. Force and displacement are vector quantities. You've dealt with many theorems in mathematics. What is a theorem? It's a general proposition that is established by a chain of reasoning, a truth that can be proved by means of accepted truths. To establish a relationship between work done and energy, we go back to Newton's second law. The equation which we use to apply Newton's second law is the net force is equal to the mass of the object multiplied by its acceleration. We'll limit this proof of the work-energy theorem to work done by a force which acts parallel to the displacement. Since the net force and the displacement are parallel to each other, theta can be taken as 0 degrees. Cosine 0 is equal to 1. Net work done is equal to the net force times the displacement times the cosine of theta. Net work done is equal to the product of the net force and the displacement. Using Newton's second law, we can change this formula to the net work done is equal to the mass times the acceleration of the object times its displacement. There are many instances when we can use the formula F net equals ma to solve problems. Just remember that we are using the net force and calculating net work when we make use of it. Let's continue. We get the net work done is equal to the mass times the product of acceleration and displacement. The product of acceleration and displacement, A times delta x, has appeared in a kinematics equation of motion. Do you remember the equation of motion? The final velocity squared is equal to the initial velocity squared plus 2 times the product of acceleration and displacement. Aha! Let's make the product of acceleration and displacement the subject of the formula. We get A times delta x is equal to the final velocity squared minus the initial velocity squared, all divided by 2. Yes, the next step is to substitute this expression into the original formula for net work done. The net work done is equal to the mass times the final velocity squared minus the initial velocity squared, all divided by 2. Since everything's divided by 2, we can write 1/2 in front of the expression to get rid of writing it out as a fraction. We can also multiply through by mass, getting mass times final velocity squared minus mass times initial velocity squared. Finally, remove the brackets. Net work done is equal to 1/2 times the mass times final velocity squared minus the 1/2 times the mass times the initial velocity squared. I'm sure you recognize that 1/2 times m times v squared is the formula for kinetic energy, Ek. The net work done on a system is equal to the change in kinetic energy of the system. We've proved this new idea of energy and work being related to one another by using Newton's second law and an equation of motion. We've done this to prove the work-energy theorem. The work-energy theorem says this: the net work done on an object is equal to the change in kinetic energy of the object. This means that the net work done on an object is equal to the final kinetic energy minus the initial kinetic energy. Net work done is either positive or negative, or of course it could be zero. If the final kinetic energy of an object is greater than its initial energy, positive work is done on the system. The velocity has increased. The system has gained energy from the net work done on it. Similarly, if the final velocity is less than the initial velocity, the system has lost kinetic energy. Negative work has been done on the system. If the final velocity is zero, the net work done is equal to the negative value of its initial kinetic energy. This is the amount of work which is done by forces acting in the opposite direction to its motion. We can think of this as the work which the object can do when it comes to rest. How does this theorem help us solve problems? Firstly, work and energy are scalar quantities. It's often easier to work with scalar quantities when solving problems than to work with vectors such as force and displacement. Let's solve a problem. A 3-kilogram toy car that travels at constant velocity for a distance of 6 meters in 5 seconds. A. What is the kinetic energy? And B. How much work is done on the car? EK is equal to 1/2 times mass m times v squared. We have the mass of the car, 3 kilograms, but we need to determine the velocity of the car. Velocity is constant, therefore v is equal to distance, 6 meters divided by 5 seconds. Its velocity is 1,2 meters per second. Substitute into the formula for kinetic energy. The kinetic energy is equal to 1/2 times 3 times 1,2 squared. The answer is 2,16 joules. How much work is done on the car during this time? The car travelled at a constant velocity. There's no change in its kinetic energy, therefore no net work is done on the car. Here's another problem. Use the work-energy theorem to solve it. A 1,500-kilogram car accelerates from rest to a speed of 25 meters per second over a distance of 45 meters. Part A. What is the change in kinetic energy of the car? Part B. What is the net work done on the car? Part C. What net force acts on the car? You can pause the video while you solve the problem. Part A. The change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. That is 1/2 times the mass, 1,500 kilograms, times its final speed squared. 25 meters per second squared. The initial kinetic energy is 0 because the car started from rest. The change in kinetic energy is equal to 47,000 joules. Part B. The work-energy theorem says that the net work done is equal to the change in kinetic energy. Therefore, the net work done on the car is 47,000 joules. Part C. The net work done is equal to the net force times the displacement of the car times cos 0. Rearranging this formula, we get the net force is equal to the net work done divided by the displacement of the car. That is 47,000 joules divided by 45 m, which gives us the answer of 10,400 newtons. But force is a vector. It needs direction as well. 10,400 newtons in the same direction. Let's try another problem. A 1,000 kilogram car traveling at 20 meters per second skids to a stop. The force of friction between the tires and the road is 12,000 newtons. Part A. What is the change in kinetic energy of the car? Part B. How far does the car skid? Pause the video if you want to solve the problem first for yourself. Part A. The change in kinetic energy is equal to 0 minus the initial kinetic energy of the car, because when the car stops, it has no kinetic energy. That gives us the answer of negative 200,000 joules. Part B. Since the net work is equal to the change in kinetic energy, negative 200,000 joules, we can calculate the displacement of the car using the formula net work equals the net force times displacement times cos 180 degrees. Friction force acts in the opposite direction to the motion of the car, therefore theta is equal to 180 degrees. Displacement equals the net work done divided by the friction, which gives us negative 200,000 joules divided by 12,000. The answer is 16,67 meters. Let's go back to review this problem. The force of friction does work on the car's tires because the car is skidding. It skids, its tires are locked, not rotating, so they remain in contact with the road surface while the car skids. If the tires are rotating, the road would not be able to do work on the tires, because every moment there is a different piece of tire surface in contact with the road. The road's not causing the tires to move over a distance. Let's now tackle an object moving at an inclined plane. A 15-kilogram block slides down a rough plane surface which is inclined at 10 degrees to the horizontal. The block starts from rest and reaches a speed of 6 meters a second when it's traveled 25 meters down the slope. Part A. Calculate the change in the block's kinetic energy. Part B. Calculate the net force acting on the block while it slides down the plane. And Part C. Calculate the friction acting between the surface of the block and the plane while it slides. Pause the video if you want to try this problem before reviewing the answer. Part A. The change in kinetic energy is given by 1/2 times 15 times 6 squared minus 0. The answer to that is 270 joules. Part B, the net force, is calculated by dividing the net work by the displacement of the block. That's 270 joules divided by 25 meters, giving an answer of 10,8 newtons. And part C, the net force is equal to the component of weight acting parallel to the surface of the plane minus friction. The component of weight is given by the weight m times g multiplied by the sine of the angle of inclination. The component of weight parallel to the plane is equal to 25,53 newtons. Friction equals 25,53 minus the net force, 10,8, which gives the answer of 14,73 newton. The direction of the friction force is up the slope. Remember that force is a vector quantity. We must specify magnitude and direction. Can you see how the work-energy theorem is a very useful tool to use when solving problems? In the next lesson, we tackle the conservation of energy. Until then, practice by solving a few more problems. It's perfect practice that builds competence. Keep working hard to achieve your goals.